Welcome to the Warwick Christmas Lectures. Tales of objects that hover in mid-air sound like magic. Join Dr Paul Goddard from the Physics Department at the University of Warwick for science that is even more astounding than a magic trick.
Hello, I'm Paul Goddard. I'm a lecturer in physics here at the University of Warwick. And in this video, I'm going to show you how, using a piece of material called a superconductor, we can make a levitating train set using this track that I have here. This is a piece of superconductor, and it doesn't look like much. However, these materials are amongst the most interesting, exciting, and most studied materials of modern times. They're called superconductors because below a certain temperature, they conduct electricity with zero electrical resistance, which means they can carry electricity and store it without any energy losses whatsoever. But they also have some very interesting magnetic properties, which is what I'm going to show you today. So what we have here are permanent magnets, amongst the strongest that you can buy, and they produce a very strong magnetic field. But look what happens when I bring the superconductor close to the magnets. Nothing interesting happens at all. The superconductor is not attracted to nor repelled by the magnets. And that's because it doesn't do anything interesting. It doesn't become superconducting until we cool it down to very low temperatures. To cool the superconductor down, I'm going to use what's in this container here, which is liquid nitrogen. Now, ordinarily, nitrogen is a gas and it makes up almost 80% of the air that we breathe, so we have access to lots of it. But when you cool it below about minus 200 degrees Celsius, then it turns into a liquid. So the nitrogen in this bucket is at minus 200 degrees C, but the temperature of this room is plus 20 degrees C. So in a similar way that an ice cream will melt if you leave it out on the counter, so the liquid nitrogen will slowly boil away from this bucket. But it won't do it until I've had a chance to use it. But I can use the nitrogen to cool things down as low as minus 200 degrees C. And just to put this in perspective, the coldest place on Earth in Antarctica can reach down as low as about minus 90 degrees. So this liquid nitrogen is very cold indeed. The properties of materials change quite a lot when you cool things down to such low temperatures. So for example, here is a piece of rubber tube, very flexible at room temperature, but when I cool it down, it becomes very hard and brittle. So in a similar way, I can use the nitrogen to cool down the superconductor and change its properties. Okay, so I'm going to use the liquid nitrogen to cool down the superconductor to very low temperatures. So it starts at room temperature, and I pour in the liquid nitrogen, and now it's dropping down towards minus 200 degrees C, where it will become superconducting. And it takes a while to get to this temperature. Believe it or not, these types of superconductor are known as the high temperature superconductors because most superconductors actually only work at much lower temperatures, for which we need liquid helium to get there. And liquid helium is a lot harder to come by than liquid nitrogen, and it's more expensive. So this particular material contains, it's complicated, but it contains the elements gadolinium, barium, copper, and oxygen. And there are a number of different materials that superconduct at liquid nitrogen temperatures, but all of them contain the elements copper and oxygen. And so as well as being called the high temperature superconductors, they're often called the copper oxide superconductors as well. Right. It should be cooled down enough now. So you remember when it was warm, it didn't do anything interesting when it was brought close to the magnets. But now it's superconducting. It turns out that a superconductor can save a lot of energy by not having a magnetic field inside it. And so it will do everything it can to prevent that from happening. So when I bring it up to these magnets here, it can defy gravity. That's how much energy it saves. But it can only do this while it's superconducting. When it warms up, it's not a superconductor anymore, and it falls back down to Earth. So what's happening here? Well, when I bring the superconductor up close to these magnets, it's producing a magnetic field that exactly matches the one it feels from below that's being produced by the magnets. But how can it do this? It doesn't contain any magnetic elements like iron or nickel. Instead, it's working more like an electromagnet. So, as you may be aware, when you send a current round in a circle, you can produce a magnetic field. And this is what's happening to the superconductor. When I bring it up close to the magnets, electrical currents are being produced in the undersurface of the superconductor that produce the field that allows it to float. And because it's a superconductor and has no electrical resistance, these currents, once they start, can flow forever, but only while the superconductor is cold. So this is pretty impressive. The superconductor floats very high above the track on a cushion of magnetic field, and it's defying gravity. However, it's not very stable. I can knock it just a little bit, and it falls off. So that doesn't bode well for us making a train set, because it won't be able to take the corners of the track very quickly. But there's another thing that I want to show you. So that superconductor was cooled down away from any magnets, but it turns out a slightly different thing happens if you cool the superconductor in a magnetic field. Okay, so this piece of superconductor here is exactly the same as the one that we were just looking at, but I put it in a little bucket so that it can stay colder for longer. And just to show I'm not cheating, there's no wheels on the bottom of this bucket. So I bring it up to the track. Again, it doesn't do anything interesting because it's warm. What I'm going to do now is I'm going to use these little spacers to cool down the superconductor close to the track so that it feels a magnetic field as it becomes superconducting. So again, I need the liquid nitrogen to do this, and it's going to take a little while for it to cool down in this bucket. So it turns out that what happens when you cool a superconductor inside a magnetic field is that the magnetic field inside the superconductor gets pinned onto little defects in the material. These particular pieces of material were made by our colleagues at the University of Cambridge to have lots of these little defects and to allow this pinning to take place. So once the magnetic field is pinned to these defects inside the superconductor, the arrangement of the magnetic field in the superconductor is very difficult to change, and it won't change by itself. And in order to exploit this, we've made this track in a particular way. So we have here on the inner rail of the track magnets with all of their north poles facing up. In the center rail of the track, we have all of the south poles of the magnets facing up, and on the outer rail it's again all the north poles facing up. So this means if you could see magnetic field, if you look across the track, it's changing a lot. It's going up and then down and then up. But if you look along the track, the magnetic field is not changing hardly at all. So now the superconductor is cold, the arrangement of the magnetic field is pinned in place. So that means if I take away these little spacers, the superconductor won't want to fall down onto the track because the magnetic field is stronger there and would require the field inside the superconductor to change. It's not going to move across the track because the magnetic field changes a lot in that direction, but it's very happy to move along the track where the field looks the same. And as you can see, it can take the corners quite quickly, which the superconductor that was cooled in zero magnetic field would not be able to do. So the fastest train in the world, the superconducting maglev train in Japan, works on principles similar to this one. And there are lots of other potential applications for superconductors, not least of which being the transport and storage of electricity without any losses whatsoever. But you can also use superconductors to make electromagnets that produce very, very high magnetic fields. And in fact, hospital MRI machines only work because of superconducting technology. There are barriers, however, to using superconductors for technology. The fact that they only work at very low temperatures is one of them, but more crucial is that for these materials that work at the relatively high temperature provided by liquid nitrogen, these materials cannot be turned into long lengths of wire, and that's what's restricting the use of superconductors in our everyday lives. There's one last thing that I want to show you. Now that the magnetic field is pinned inside the superconductor, as I said before, the superconductor doesn't want to fall down onto the track where the field is stronger, but equally well, it won't want to fall away from the track where the field is weaker. So we've set this up correctly. I should be able to turn it upside down. Pretty amazing. So, although this effect is known as superconducting magnetic levitation, what is actually happening is the superconductor is just stuck in place at the distance away from the magnets at the point at which it became a superconductor, which is when I cooled it down with the liquid nitrogen. So it may surprise you to know that although we know exactly what happens in most superconductors, these ones, what happens in these materials that work at the relatively high temperature provided by liquid nitrogen, we still do not know exactly how these materials work. Many physicists, like myself here at the University of Warwick and all over the world, spend their time thinking and doing experiments trying to figure this out. This issue of how this high temperature superconductivity works remains one of the most pressing problems in modern physics. And I don't think that this problem is going to be solved anytime soon. So if you're planning a career in science, then maybe you can have a hand in figuring it out. Thank you.